Welcome to section 13.8, extrema of a function of two variables. This is an expansion on the concept of extrema in AP Calculus, where we work with curves. And actually, two of the theorems we're going to see in this section are related to previous theorems that we've studied in previous classes. The first one is the EVT, so extreme value theorem, and the second one is connected to the second derivative test, and this time it's called the second partials test. So the goal is the same as in regular calculus of one variable. We're trying to find where a function reaches its maximum or minimum. There's also relative max and relative min, as well as absolute max and absolute min. In AP Calc AB, the extreme value theorem states something very simple. It says that if a function f is continuous on a closed interval, then it has both a max and a min. The extreme value theorem here now, with functions of two variables, is very, very similar. It says that if f is a continuous function, and it is defined on a closed region, so that's the equivalent of a closed interval, but it's a region, so because the domain is dependent on x and y, it could be a circle, for example, or a disk, I should say, a closed disk, then there is at least one place where we find a minimum and a maximum. The idea of relative min, relative max, absolute min, absolute max extend naturally. It's the same notion. The highest of everywhere is the absolute max, and then if you have smaller, lesser peaks in other places, then they are relative max. So we're going to define a critical point, and once again you're going to see that it is very similar to what we knew from regular one variable calculus. If a point on a function is such that the two directional derivatives are both equal to 0, then it is called a critical point. Or if you have a situation where either fx or fy do not exist, or both of them, then it is also called a critical point. So once again, this is similar to what we saw in regular calculus. If the derivative is 0, or if the derivative does not exist, then we have a critical point, provided the point exists. So just a quick comment on regions. Open regions are like open intervals, so the boundaries are not included, and we would sketch that with dashed lines. So here this is an open region, it's the circle, but we kind of peeled off the skin, if I can say. So it's x squared plus y squared is less than 1. A closed region would be the same, but with the skin on, so x squared plus y squared is less than or equal to 1. So in an open region, we can only talk about the interior, and that's where we use the notion of critical points. When we have the extreme value theorem in regular calculus, we always have to check the extremities of the interval separately. It says that the extreme value happen at a critical point or at the end point of the interval. In 3D here we will have the same issue of when we have closed regions, we're going to have to separate the inside region and study that, and then we will have to study the boundary separately to find any extreme value. So what that means is when we have an open region, it is a little easier to figure out extreme values. However, we only find relative extrema. We are not sure if they are absolute extrema, because the function, for example, might just be going higher and higher to infinity, so there are no extreme values, and that's a little bit harder to figure out. But for relative extrema, we will use the extreme value theorem that was given above. So in the example of a function here, 2x squared plus y squared plus 8x minus 6y plus 20, the domain of f is all of the xy plane, and so it is an open region. There is no boundary that closes it. We take the two partial derivatives, fx is equal to 4x plus 8 and fy is equal to 2y minus 6, and we need both of these to be equal to 0. Quite obviously, this leads to x equals -2 and y equals 3. So here we have a critical point. If we plug that critical point back in the function, we find that f of -2, 3 is actually equal to 3. Now we would still need to figure out whether this is a relative min or a relative max. And in 10 minutes or so, we'll have a better strategy to find that. For now, let's just note that it is not enough, like in calculus, to say that, oh, f of x changes from negative to positive and f of y changes from negative to positive, therefore it's a minimum. There are cases where the two things I just said are true, and yet it is not a minimum. I can show you an example right here. It's not necessarily easy to see, but like the critical point, which is over there, is a saddle. But if we look in the x and y directions from the top, so this is what I'm trying to do here, in fact, both it goes up in the x direction, it goes up in the y direction, yet it is not a minimum. So there are interesting cases where fx changes from negative to positive and fy changes from negative to positive, and yet it is not a minimum. The example we are talking about in this exercise is this function here, so we can see that it's a minimum thanks to the graph. But if we didn't have the graph, how would we do it? Well, as I just said, we will have a better or a more general, powerful strategy in 10 minutes. For now, what we can do is notice that the expression we are given here, we can actually use completing the square to rewrite it. And if we do so, we find that f of xy is 2 times x plus 2 squared plus y minus 3 squared plus 3. Notice how this term is always going to be greater or equal to 0 since there's a square. Same for this term here, y minus 3 squared cannot be negative. And then we have plus 3. So the entire expression is greater or equal to 3. Why is that interesting? Well, the critical point we found earlier is actually a point where the z value is 3. So we know that this has got to be a minimum, right? Everything is greater or equal to 3, so we found a minimum. It's a relative min, and in fact, because of this, we can even testify that it's an absolute min. All right, so just a little comment about the way we answer a question. If a question is find the maximum, find the minimum, or what is the maximum, what is the minimum, then we are talking about the z value. If we ask where is the extreme value, where is the max, where is the min, then we are asking for the x and y coordinates, so the value in the domain. Okay, so the difference between what and where. Here's a similar second example. Again, f of x and y is defined over all real numbers. There's no limitations, and we can see that any value of x and y, we will be able to plug them in. So, same strategy, we take the derivative and we look for where f of x is equal to 0 or f of y is equal to 0. If I look at this expression, it may feel like, oh, if x equals 0, then that's going to be 0. Great. And if I look at this expression here, if I have y equals 0, then f of y, the first partial derivative in terms of y, is going to be 0. So it looks like we have found a point, the point 0, 0, that is a critical point. Well, it is a critical point, but we have to look back. If both x and y are 0, now we have a different problem. We have the problem that we are dividing by 0 as well. Same here. So it's not that we have a point where the partial derivatives are 0. We are in a situation where the partial derivatives are actually undefined. But In a case like that, it is also a critical point. If fx is undefined or if y is undefined or both of them, it's still a critical point. So 0, 0 is a critical point. If we plug 0, 0 in the function, we find that it's 1 minus 0, so the extreme value is z equals 1. Once again, by observing the expression, we will notice that x squared plus y squared is always going to be a non-negative number, and then taking the cube root is still going to be non-negative. So if we do 1 minus something non-negative, it's always going to be less than or equal to 1. It's written here. And therefore, we can conclude that f of 0, 0 equals 1 is an absolute or relative max. Now, yeah, it's both a relative max and an absolute max. I want to show you this function. It looks like this. We can see the axis here. So there, it's a pointy surface, and the point 0, 0 equals 1. The point 0, 0, 1 is up here. In this exercise, we are looking for the absolute extrema on the closed region given by these two inequalities. And that means x is between 0 and pi, y is between 0 and 1, so it's a rectangle. And the function we're trying to find the extrema for is f of xy equals sine of xy. I will zoom in a little so we can see better. So what we do first is we would want to sketch the region that we're looking at, and it's this red rectangle. So because this time it's a closed region, it's less than or equal to everywhere, we are going to have to split it into two cases. The first case is what's inside, basically the open region, and then secondly, the boundary around the open region. So just like in regular calculus, we were looking for critical points in the open interval, and we were then also separately looking at the endpoints. Because when a function is suddenly cut, we may find an extreme value there that wouldn't be there if the function wasn't suddenly cut. We'll see at the end of this exercise that it happens here, in fact. So for the inside area, the open region, we look for the critical values just like before. So first we find the first partial derivatives, and we note that it's never undefined, so the only case we are interested in is when they are both equal to 0. There are two possible answers. The first one is at 0, 0. Indeed, if x equals 0 and y equals 0, we will find that both of these expressions are equal to 0. However, and that's not something you may always notice when you're solving an exercise, but if you're really paying attention and very careful, you may notice, oh, this is not in the open region. This is on the boundary. So we won't care about that too much now because it is not inside the boundary. We will see this in the second part. But this is the first possible solution. The other possible solution, if this equals 0 and that equals 0, is that cosine of xy equals 0, right? That would also lead to these two first derivatives being 0. Therefore, this happens when x times y equals pi over 2. If this is pi over 2, f of x, fx of xy will be 0. So, in the domain, that is any point such that xy equals pi over 2, or we could say any point in the domain such that y equals pi over 2x. What is the value of f at these points? The value of f, if I plug in xy equals 0, xy equals pi over 2, is simply sine of pi over 2, and that is equal to 1. This is sine of pi over 2. Because xy equals pi over 2. So on the figure for the domain, we can start sketching the curve y equals pi over 2x. It's done in blue here. We don't care when it's not inside the region, but suddenly here we have all these points that are interesting. They are some kind, maybe, of extrema. They are relative extrema, most probably. Are they maxima, minima? Are they absolute extrema? We will figure that out later. It says here that it's a max, but this is not something at this point that we would be able to figure out. All right, so the second part is to look at the boundary. And the boundary of this rectangular region can be split into 4 parts. We have y equals 0, y equals 1, x equals 0, x equals pi. Y equals 0, y equals 1, x equals 0, and x equals pi. These values come from the way the region was defined here. So if y equals 0, now our function f of xy, which is sine of xy, is just sine of 0. So along the horizontal line y equals 0, all the outputs are z equals 0. If y equals 1, then f of x1 becomes sine of x, because it's sine of x times y. So that's a little tricky. We now have a function of one variable, sine of x, in the interval from x equals 0 to x equals pi. And we luckily have a function that is not too hard to study. We know that this, if sine of x equals 0, then the output is 0. Likewise, if sine of x equals pi, the output is 0. And in the middle, at x equals pi over 2, the output of sine x is 1. So this is summarized here. These are the 3 interesting points along the line y equals 1. So along this curve here, if I take a slice like this, it starts at 0, it goes up to 1, and then it goes down to 0 again. And interestingly enough, we knew about this 1 here, because that point is part of the curve y equals pi over 2x that we talked about earlier. So it's no surprise that we have a value of 1 up here, because it's part of this curve. And most probably we're going to find a value of 1 here when we study the line or the boundary x equals pi. So we'll see if that is true in a minute. Then, if x equals 0, f of 0y is going to be equal to sine of 0, and it's 0. So again here, all the surface is at a height of 0 along all these points, and these points as we saw earlier. Finally, the last boundary is x equals pi. So if we plug in x equals pi here, we get sine of pi y. Now that's interesting. How is this going to behave when y goes from 0 to 1? Well, if y equals 0, we have sine of 0, which is 0. If y equals 1, we get sine of pi, which is 0. And somewhere exactly in the middle, actually, when y equals 1/2, it's going to be sine of pi over 2, which is equal to 1. So all of those are found here. So we have a similar shape. The surface is at 0 here, it goes up to 1, and then it falls down to 0 again. So we found everything we are interested in. We found that the surface is at 0, 0, it curves as a sine up to 1 and then back to 0 down here, and it curves up to 1 and goes down to 0 along this side of the rectangle. And here we have kind of a crest that is always at a height of 1. The good thing about absolute extreme values is that we can just compare all of them. And we notice that along this crest, it's z equals 1, and then we have other values, extreme values, that are zeros and ones everywhere. So all the ones are the extreme max, and all the zeros represent the extreme minimum of the surface. And where these occur, we discussed already. So the absolute max is f of xy equals 1. The absolute min is f of xy equals 0. Where, here, and where, here. So let's have a look at this. Let's have a look at what this looks like with a proper graph. This is the surface that we were studying. So from the top, you can see it is a rectangle. And we saw that the surface is 0, 0, and then it goes up and down to 0 again, and here it goes up and down like that. So this is the shape. So the point right there, it looks like it doesn't reach 0, but it actually does. That's just the limit of the grapher software, but it goes all the way down. This point that's all the way down that we identified as a minimum is not special if the surface had continued beyond the rectangle, because this would just the surface just continues to drop after that in the negatives. It's only special because we have a closed region, and this is why when we have closed regions we have to look at the boundary, just like in regular calculus we had to look at the endpoints separately. Okay. So I said earlier that you can't just say that fxx or fx changes from negative to positive and fy changes from negative to positive to declare that we have a minimum, for example. There is the equivalent of the second derivative tests for functions of two variables. It's called the second partials test, and here it is. Now, there's no proof for that. In fact, even in the textbook, they say that a proof is best kept for a class of advanced calculus. So we will just receive this equation and apply it in order to figure out whether points are relative min, max, or saddle points. This is just what it is. We need to calculate d. And how do we find d? We need to calculate the second partial derivatives, fxx, fyy, and fxy, and just plug them in at the point ab that is a critical point and see what comes out. If d is positive and fxx is also positive at that point, then it's a relative min. If d is positive but fxx is negative, then we have a relative max. And if d is negative, then it's a saddle point. There is a situation if d equals 0 where the test is inconclusive. In the second derivative test, I think there was a similar issue that was possible where the test was inconclusive. In fact, I believe that if you pick a point from the previous exercise along this crest here, if you pick one that maybe has decent numbers so that it's easy to plug in, you would find that the test is inconclusive. So it wouldn't be able to tell you that this is a relative max. Luckily, in most cases, this doesn't happen. Here we have an open interval. Here's the function. It already looks like this function is not going to cause much trouble. So we look for the critical points by setting the first partial derivatives equal to 0. And after a little bit of work, we do have a system of two equations in two variables. So sometimes it's a little harder. It doesn't just throw the solution directly at us. We have to work more. But we find that there are two critical values, 0, 0, and 4 over 3, 4 over 3. So we can calculate the rest. The second partial derivatives give us fxx equals negative 6x, fyy equals negative 4, fxy equals 4, and now all we need to do is plug in the values of x and y. There's only one place where it's actually going to matter. So at 0, 0, x equals 0, and this becomes negative, so it's a saddle. At the point 4 over 3, 4 over 3, we plug in x equals 4 over 3, and we find that d is positive. On the other hand, fxx is negative, so it's a max. So that's it. It's a pretty intense section, just like in calculus, it was not always easy to find these maxes and mins, but it's an interesting section and it feels quite applied, I guess. Thank you.